So how are you today? Perfect. All right. So we're gonna do nucleophilic. Acid substitution. So here's one thing. Can try. And then we have thionyl chloride. So if you look at this one over here, this is quite similar to what we already did for the alcohol. So if you look at this one here, this will be replaced by chlorine. So the trick is the, do you guys remember, do you remember this one? We have this 4 living groups on the, this carboxyl group here. But this will bond to there, like this, and then later this will be very good living groups. That's why they're gonna attach to here. This group. Okay. So this is how you can have a acid halide by doing this one. Okay. Do you remember this? Okay. So the only thing is that it's a carboxyl group instead of the alcohol, 100%. And there's quite a thing you can do. Is if you have some carboxylic acid, maybe 2 of them, and you can try to heat it up like very high temperature over here. So then they can form acid anhydride. So what happens to here is if you have 2 of them, here, and this bond to there, and those will come out. So be watered. Okay. So if you treat your carboxyl group with a very high temperature, you may have some anhydride form at the end with water. Because of those 2 interaction on those carbons, and those water will just come out. So this is something you can do. So interestingly, you actually do this the other way. So if you have a acid anhydride form over here, you can do hydrolysis. So meaning you use water to break this one in half, and there's 2 separate carboxylic compounds. So it's actually the other way. Make sense, right? Okay. Good. All right. So then the next one, okay. So we have carboxylate. And then we have some hydromethane over here. Okay, so what happens to this one is this will actually going to attack this one because this hydromethane has halogen on other side. So this will be very electron rich, and then this is electron poor. So this will attack on this carbon here. So they can form methylbutanoate, D and AA. This one. Yeah. Okay. So maybe can you try this one real quick? So it will be, oops. Okay, yeah, perfect. Okay, how about this one? We have maybe enjoy. Let's see. So this is a carboxylic compound, and you can treat with this alcohol. Okay. Some alcohol. Okay. So in this case, what you can do is this one will goes to here. Okay. But before it goes to there, it has to be treated with some acidic condition, because this oxygen here will catch the hydrogen cation. So that becomes this one, and then even though this is not so strong nucleophile, but because of this so electrophore, and that goes to, okay. And then it goes to there, okay. And then when it's to bound to here, this is positive charge, right? And then this hydrogen goes to this one. This one. And then this is picked up by some base. Okay. So this is gone. So it'll be negatively charged, right, like this. Okay, and this, so when hydrogen taken to the here, positive goes to here, and this, the one of the lone pair goes down here again. So this will be, then, and so this will be really good leaving group because it's water, so it goes to here. So eventually, you're going to have this one. Okay. Does it make sense? Okay. So the point here is when it treated with acidic condition, this makes very electron poor on this carbon. That's why this is not so good nucleophile because neutral still do that. Then once that hydrogen catch by this hydrogen part on the carboxylic group, they are better leaving groups. They will leave. Okay, that's the key. So maybe can try methane instead. Maybe here. And you can try. Yeah, same. And acidic conditions. Yeah, just okay, so yeah, so it's right. Okay. Okay. I can move on, right? Okay. All right, so the next one is if you have some carboxylic compound also again, and you can treat with some compounds in the meat here. And then in this case, we're gonna use the DCC. So DCC looks like this. Nitrogen, carbon. It's yeah. Oops. looks like this one. And then what happens to this one is this one, DCC, actually catches the one hydrogen over here. Well, previously this the tab electron goes on here. Okay. So this is the negative charge, right? And then this goes to the carbon. And then it goes to carbon. Okay. And it goes to carbon, and this is gone, right? And then this will come to on this side. So then goes to here, goes to R over here. Okay, let me show you. And then this will be positive charge, and when it goes to there, it goes to the up. Okay, so this will be gone. This is the negative charge. Okay. And then this pushes down to here again, and this goes to there. And then this one pick up another hydrogen over here. Form. So this is catching the protons, actually the AC over here. And then eventually, what they're gonna form is this one. So you're gonna have this one as a byproduct. So you see, there's one of the hydrogen is catched by conjugate base when it pick up another hydrogen and does so this is after we trigger the DCC coming from there, but this is our desired product. So that's it. Does it make sense? Did I? Yeah. Okay. Okay. So then let me try some practice problem. I'll give you some practice problem. Can you try this one? But okay. 2, and we're gonna try with the DCC. Cyclohexyl copper diimide. This is so we can try to get this one. You got it. Okay. So, yeah. Okay. So you can compare. So you have this one over here, right? This one goes to the DCC. Yeah. So if that does that, you only need to do is just remove this one, and you put this one on the amine group side first. So we would, and you only need to delete one hydrogen. Okay, so one hydrogen here, and just copy 3 carbons next here. So that's it. Try one more. Okay, try one more. So let's say we have this one, you got the trick now, right? So just remove this one here. Put in, but just remove one, so we just one. Just 2 carbon there. That's it. Okay. Mix. Okay. Good. All right. So the next one. This is the next one. Okay, so we have carboxylic groups. Over here. You can. This is what we did already in the previous chapter. So if you do this one, you know this will be aldehyde. And then if you actually keep going, you can actually have this one. This one. Okay. Icoxide. Because this is what we did before in previous chapter, but you have a sequential hydrogen shift on the carbon on the carbonyl groups. That pushes the electrons up there. Okay. So this is where we have right now, but you can also treat that with some acidic condition, and then this oxygen in this compound will catch the proton, so they become alcohol. So whenever you do this one, actually this aldehyde form is so like inks in time form and just move on to the next step right away. So we don't normally see this one, but this one. And then when you put it in the acidic condition, it will be protonated on this oxygen. So it will become alcohol. All right, let's try the practical problem here. So so maybe you can try this one. Okay, so yeah, you got the trick. So only thing you have to do is this one. So it's actually this oxygen is the one that get the alcohol part, but doesn't matter. The trick is just better. This one. Okay. I can move on, right? All right, so then the next one, okay, we have, this is also same thing, pretty much. We can also treat it with the phosphorus tribromide. And then what they do is that they're gonna form also the ones with the better living groups. Then tap over here. So eventually they can form acid halide. So from the some carboxylic acid compounds, you can treat with some phosphorus tribromide, and you can have some acid halide compounds from there. So maybe just one quick practice you can try is. This one real quick. Okay, so it's pretty good, right? Just A. Okay, so because this can make the barren leaving group of the this O part and leave when they have a inner part just goes there to replace it. All right, so the next one is the okay. So whenever we have this acid halide form, you can treat it with some water. So what happens to this one here is if you have the lone pair, it goes to tech here because not just by the oxygen and carbonyl group, which is very electron poor carbon they're making in here, but also halogen group is also very electronegative. So even though water is not so good nucleophile, they're able to attack on this carbon because this carbon is very electron poor point. So when they do that, they form like here. Like this one, okay? Because they now have a lone pair donated to this carbon here, right? So that makes the push on the carbonyl group bond here, so it goes to there. This will be negative charge. And then now the water pick up this one, so it goes to there. And then this will be gone. The charge here. And when this push down to the original carbonyl group, so negative charge will be gone. And so this core is also, relatively speaking, pretty good leaving group. So whenever you have that, the water to grab the hydrogen, they have protons with the chlorine can form. Let's see. So the trick is you can try to detach the halogen group and replace by water, but without the protons. That's the key point. So acid halide treated with water that will hydrate to the form carboxylic acid. So maybe try this one real quick, and we'll just move on because I don't think this is very difficult. Yeah, just this one real quick, and we'll move on. Okay, yeah, you done it right. Good, perfect. So just pretty simple trick you can do. Just put OH. So OH actually water initially, but because they're deprotonated later, the hydroxy group, so they become just the carboxyl. It's pretty easy trick. All right, looks good so far. So the next one, okay. So whenever we have a carboxylate, form some salts with some metal cation over here. You can treat with some the acid halide compounds like this one. Okay. All right. So in this case, it's pretty much the same thing we're gonna do. Okay. So if you look at these two, obviously this carbon is very electron poor because of the oxygen and the chlorine. So this is also quite not so basic, but some are good nucleophile. This goes to there. Okay. And then that makes the push on oxygen, so negative charge, will push back down here, become neutral again, becoming carbonyl group originally, and goes back. So if you do that, this will be what? Then this Cl minus, so this will become acid and hydrogen. Okay, so does it make sense? Okay, good. So maybe you can try this one example real quick. And then you can try the try to make it simple. And you can have this one. Let's make it even smaller actually, so it's all better. The one actually make it even simpler. So it's like this one's better. Oh, good. Oh, perfect. So yeah, I'm gonna do the super trick. Let's do. Yes. So if you redo this one. Yes. Okay. All right. I can move on, right? Okay. So the next one. Okay. So you can treat the acid halide compounds with some alcohol. Okay. So we have some cyclohexanol over here. And then what happens here is it's pretty much the same. As I told you before, even this one is not so strong nucleophile. It's neutral, but because of this carbon is so poor in electron density, so this goes to there. And then it goes to there. So this will become positive charge bound to this one. And it goes to negative, so it'll be single bond again. And then this electron pair goes down again, so it'll be neutral, carbonic groups. And there goes leave. And then later, this hydrogen catch this one, so this will become neutral. So this will be gone as HCl. So if you do this one in total, so you keep this carbonic groups, and then you have to put a bond, this carbon bond to the oxygen here, and losing the deprotonated, and then there's this. So this form ester group, ester group. Okay. All right. So let's try just one more problem. It's pretty much the same. But yeah, I just want you to know the trick, that's all. Okay, so if we can do okay, yeah, that's good, right? All right. So You actually have one more I want to show you. This is the bit tricky. So you have this one here, acid halide, and you have diol. Looks like this one. Okay. So in this case, the tricky part here is you have two parts you can do when they do come interact each other. In this case, you need to think about the degree of the alcohol. So if you look at this hydrox group, this alcohol part, this carbon has a 2R. So it's just like a secondary alcohol part right here. And then if you look at this one here, this will be primary because this carbon only has 1R over here. This carbon is 1R. So if you have a choice, whenever you have the primary or lower degree of the alcohol will be more reactive. And this is a less reactive. Because of the bulkiness of the compounds where you have a hydrox group, it kind of hinder the reaction between acid halide and the alcohol. So when you draw the major products from this one, not this one, but for this one, you can use this kind of stay the same. This one goes to this one. So not this one, but this one will actually go to here and make this one leave. And that's why you got this part here, onto this one, not here, on the major part. It's because of the space problem. It's more higher degree. It has some bigger compound. There's not so much space. This will be more free. This can approach to this one than this one. That's why this will become your major products. Does it make sense? Oh, okay. Maybe you can try this one real quick. Okay, so let's check. So did you choose this one or this one? This one, right? Perfect. So when you do this one actually to here, not this part. So then you just going to have this one just stay the same most of the time, and this oxygen move on to this one because there's two. This will be the major. Makes sense, right? I think, yeah. Okay. All right. So there's a couple more to go today. All right. So whenever you have some compounds, acid halide compound, you can treat with some ammonia. Okay. But let's say there are two. Okay. So I'm gonna say. So this ammonia groups will attach to, once again, the carbon right there. Okay. And then they actually move this one again and pick up the one proton here. So become neutral. So I'm sorry. This another ammonia will grab this one. So that's why there's two. So twice much of the ammonia should be there for the equivalent amount of the acid halide compound. So when they form, ammonia goes there. I'm sorry, I'm going to explain. So ammonia goes there because it's the chloride, it becomes positive. Okay. So then one of the hydrogen will pick up by another ammonia. So they become ammonium cation. Okay. So when they push, they pair up with the anion. So we call ammonium chloride. And this is why they only have two hydrogen there called anion. So this will become this one. Makes sense, right? Does it make sense? Okay, good. All right. Can you try this one real quick? Do real quick and then we'll move on. Okay. So yeah, we get good trick here, right? Can do this one. Okay, that's it, right? All right, so just one more. Okay, so if that is the case, let's try to do this one. Okay. So how about we have this one. Okay. We have a dimethylamine. So this is over here. So only thing you have to do is this one bound to nitrogen will attack here, and this one will be picked up by another one. So there will be also two equivalent amount of this one for one of this. So this will be bound to here. So the final product will be looks like this. Okay. And then hydrogen picked up by the other one. So 2 plus 0 minus. So only difference is I just replaced the other two hydrogen as just a methyl group, and this hydrogen picked up by another dimethylamine, so they form a salt, and just you have a nitrogen with the two. Yeah, it's almost same, right? Almost same, because either just three hydrogen, either you have ammonia or the methyl group. That's the only difference. See, this could have. So I'll finish it today.